Okay, physics fan, let's brush up on some of our graphing techniques and strategies. You probably recall that all graphs contain an independent and dependent variable. If you think about you being growing up and independent, you no longer need help, so you're just kind of doing your own thing. And that's kind of what the independent variable is on a graph. Remember, it's the variable that the researcher manipulates, meaning that something like time or that we're just taking, but it's just ticking along. But we always put that on the x-axis, which we know is the horizontal axis. The dependent variable now is something that's going to change because of the independent variable. So maybe position is going to change as time changes, or the temperature will change, etc. But that dependent variable that changes because of the independent variable is on the y-axis, which is the vertical axis. It's important to remember to always label each axis, not just as x and y, but also with the variable, maybe it's distance, and also the units, so maybe it's meters. Otherwise, it's just a weird drawing with no actual description for anyone to understand. Don't forget, when you're making your graph, to determine the range of your data, meaning that you should try to fill up the whole graph when you're actually plotting your data. The reason for that is when we spread out our data, we can sometimes see trends even more so than if it's all smooshed together. So don't forget about that. And also, in a graph, the individual lines, the little tick marks, they have to be in equal increments. So maybe you make them in increments of 5, etc. The idea, though, is it's important to keep it in equal increments, or else your graph won't come out well. And of course, you have to title your graph. We often use y versus x, so something like distance versus time. Now, that's an easy way to do it, but don't forget, though, people need to know what the graph is actually about. Be sure to plot your data, and when you do so, we just plot with data points. And often we may draw a line of best fit if there is a linear relationship between the data. The line of best fit now is just going to be an estimate of basically the average of all the data points. Please understand that the origin is not always included, so it doesn't have to come through this very 0, 0 point. All right, and sometimes data is really scattered and it's really hard to see where a line could go. We can use a ruler to estimate it, but sometimes we just need to use an actual program like Excel to help us out with that. The idea is not to force a straight line, though. Sometimes data isn't in a linear relationship, and we'll talk about that later. Here's an example of a position versus time graph. Note to self, there is a title. Everything is labeled with proper units, and even though the data is a little scattered, we did draw in a line of best fit to kind of average out that information. Here's another example. It does have variables, but it's a little weak. There's no title at the top and that, but even though the data is scattered, we do have a line of best fit, and that's going to give us the average. Notice that line of best fit did not go through the origin in this case, though it's technically not the origin because it's at the year 1900 and 0. But keep that in mind, it doesn't always have to go through this little spot. Graphs can have all different kinds of relationships, and we're going to go through them. Something like this is something we'll run into quite a bit, and these guys as well. But as we go through the class, you'll start to see the relationships and why graphs are actually really helpful instead of just something to do like busy work. We can actually extract information from them. If the data is directly related, that usually means that as one goes up, the other one goes up. So in this case, its time increases, so does the position. So therefore, data increases on this straight line. Often we can refer to that line as y equals kx. You might be more familiar as y equals mx plus b. Of course, there is no y-intercept if you started at the point 0, 0, but keep that in mind. If you're inversely related, that means as the independent variable increases, the dependent variable decreases. So as one goes up, the other one goes down. We often refer to that as y equals k divided by x for the equation of that line. Sometimes it's not just growing as one goes up, the other one goes up. It's a parabolic relationship at times where there's some exponential growth. We'll see this sometimes when dealing with acceleration, when an object is speeding up. More to that and more about that later in the year. And sometimes there's absolutely no relation. As time goes on, the dependent variable doesn't change at all. It just stays constant. Now, our favorite word, slope, is something that you've done in classes many times. But slope is very important to us because it can extract information. You already know that the change in y over the change in x is what gives us our slope. But slope here can mean something. For example, a position versus time graph, when you take the slope, actually gives you meters per second, which is velocity. And for a velocity versus time graph, the slope can actually give you meters per second squared, which is the units for acceleration. Occasionally, we'll find the area under a graph. And when we do that, we'll break it up into little parts so that it makes it easier for us to figure out the area. And that might be through a series of rectangles, triangles, etc. But the area under a velocity versus time graph will actually give us our total displacement. And the area under an acceleration versus time graph will actually give us the velocity. And to do that, like I said, you just use your rectangles and triangles to figure out exactly what the area is. So we'll get creative and clever with that in an upcoming lab. Here's some pictures of what I mean. For example, under the velocity time graph, we broke it up into a triangle, a square, and a triangle. And through that, we can actually figure out what the area means. In this case, you'll find that it means, since it's meters per second, which is velocity, times the seconds will cancel out, and it'll just give you displacement or distance for the area underneath. Same for the area under an acceleration versus time graph. Since acceleration is meters per second squared units, which you'll learn later in the year, times time, one of the seconds cancel, and what you're left with is meters per second, which we know is velocity. That's just a little intro and start and reminder to graphs, but thanks for listening. Keep up the good work, and in no time we'll be ninjas in the graphing world, but also start to see and recognize the use of graphs as not just busy work, but helpful tools.